study cubical expansion. Clear? So we have discussed linear expansion, I know. Linear expansion. So this is one dimensional. Next, the area or superficial expansion. Clear? Area or what? Superficial expansion. This is two-dimensional. And the third is cubical, or this is also called volume expansion. So we are going to discuss cubical expansion. So this is three-dimensional, okay? In case of linear expansion, we have alpha, that is coefficient of linear expansion. Here, this is alpha, and the value of alpha is very small. And for superficial expansion, we have beta, that is coefficient of superficial or area expansion. Here, and the value of alpha, value of beta depends on nature. Clear? That depends on nature of the material used.
सर
Yes.
अहिलेको पेजको छैन देखाइदिनु न एकचोटि अहिलेको पेजको लास्टको
I will show you, okay, in the next slide. Clear? So I'm discussing it once again. Clear? So alpha and beta are very small. Clear? And the value of alpha and beta depends on nature of the material used. Now we are going to discuss cubical expansion. I mean cubical expansion discuss गर्दैछौँ. Okay, let me clear this page only. Cubical expansion. Now, for cubical expansion, let us consider a solid. For example, I'm taking a solid. So we have a three-dimensional figure. So we have a solid. Clear? We have a solid having original volume V1 at temperature T1. Clear? Now let us heat this solid to temperature up to T2. Clear? So we are heating this solid so that volume of the solid increases. Okay, there is change in volume. Clear? So there is change in volume, or the volume of the solid increases, and let V2 be the final volume of the solid at temperature T2. Clear? So we can write V1, this is original, or this is initial volume of the solid at temperature T1, and V2, this is final volume of the solid. Clear? This is final volume of the solid at temperature T2. Clear? Now let us find the change or increase in volume. Now we can write, clear, the increase in volume, the increase in volume, and we can denote it by symbol delta V also. Here, this is delta V. This equals V2 minus V1. So let me highlight this. V2 minus V1, the increase in volume, that is delta V equals V2 minus V1. So we have this. Now, similarly, we can write the increase in temperature. Since we are heating the conductor, so I'm writing temperature in very short. Increase in temperature, delta T equals T2 minus T1. Clear? So we have this. So I'm highlighting this expression. Now what we find experimentally, clear? Experimentally, we find that as I said in the previous lecture also, find that increase in volume, so that is delta V, we can write in this way, V2 minus V1 is directly proportional to the original volume. Clear? So that is, we can write delta V proportional to V1. Clear? I can also use V2 minus V1. Clear? So I'm writing in very short. Next is directly proportional to the increase in temperature. Clear? So we can write that is delta V proportional to, we can simply write delta T, we can write delta T also, or we can write T2 minus T1. Clear? Now we need to combine these two expression, or we need to combine these two factor. So we write combining 1 and 2, we get delta V proportional to B1 times delta T. Now we need to remove this proportionality. So when we remove proportionality, we have to introduce a constant of proportionality, and the constant of proportionality is gamma for cubical expansion. So we have alpha for linear expansion, we have beta for superficial or area expansion. Now we have gamma. Clear? So this is gamma. Clear? We are using the symbol gamma for cubical expansion, and gamma times B1 delta T. Clear? So let me write in this way, gamma times B1 delta T. Clear? Now what we do, this gamma depends on nature of the material used. We know from the previous lecture also, alpha and beta also depends on nature of the material used, whether you are using an iron, or you are using a copper, or you are using a brass. So gamma, let me write over here, gamma depend, clear? This depend on nature, depends on nature of material. depends on nature of material. Now, what is the unit for gamma? We need to know the unit for gamma. So this is a very simple expression, clear? So we can simply write gamma equals delta V divided by B1 delta T, clear? Now what we find, volume, the unit of volume in numerator and denominator cancel, so that the unit for gamma, so let me write over here, the unit of gamma in SI is per Kelvin. Clear, sir? In SI, the unit is per Kelvin. Now, gamma is called the coefficient of cubical expansion. We call gamma coefficient of cubical. It is called coefficient of cubical expansion. Clear? Gamma is called coefficient of cubical expansion. Now we need to simplify this expression. Clear? We need to simplify this expression. So for this, sorry, let me erase this. Okay. So we are going to simplify this expression, clear? So we have this delta V equals gamma times V1 delta T. So we know delta V is V2 minus V1. So this equals, we can write gamma V1 and delta T is T2 minus T1. Okay, this is T2 minus T1. Clear? T2 minus T1. Now let us write in this way. V2 equals, we can take V1 on left hand side. Clear? This is a very simple mathematical expression. So on taking V1 as common, we can simply write directly 1 plus gamma times, okay, let me put this in this way, gamma times T2 minus T1. Clear? So this is the final expression, and this expression is used in various numerical problems. Clear? So we have final volume. This is the final volume. This is the original volume. Clear? And this is coefficient of cubical expansion. And this term represent the increase in temperature. Clear? Okay.